Welcome to Slumbertainment. Get comfortable, close your eyes, and let yourself relax. Tonight we explore the history of aircraft. Please like and subscribe for more restful content. Now, let's begin. In the stillness of the early dawn, before the first hum of engines filled the skies, humanity's dreams of flight began as quiet thoughts against the vastness of the heavens. For centuries, people looked upward and wondered what it might feel like to drift among the clouds, to see the curve of the earth from above, to slip free of gravity's pull even for a moment. These imaginings were more than fantasies. They were the first steps toward the science that would one day transform the world. The story of aircraft is one of persistence and observation. It begins not with machines, but with the natural world. Birds became the earliest teachers. Their wings, hollow bones, and effortless glides were studied by curious minds who saw in them patterns to be understood rather than mysteries to be admired. Ancient thinkers like Aristotle and Leonardo da Vinci wrote of the principles that might govern flight, linking motion, air, and pressure in theories that were elegant if not yet complete. Da Vinci's sketches of winged machines captured both art and science, a vision centuries ahead of its time. Yet his designs would remain grounded by the limits of materials and power. As the centuries passed, experimentation grew more methodical. The study of air itself became a science. By the 17th and 18th centuries, thinkers such as Galileo, Newton, and Bernoulli began defining the invisible forces that make flight possible. Bernoulli's insight that faster-moving air creates lower pressure would later form a cornerstone of lift, though its full implications took time to unfold. Engineers began to grasp that wings did not need to beat like those of birds. Instead, they could use steady airflow to generate upward force. It was a subtle but vital realization, one that separated myth from mechanism. The first true ascents into the air came not from wings, but from balloons. In 1783, the Montgolfier brothers in France sent a great sphere of hot air drifting into the sky, carrying passengers above the rooftops of Paris. The world watched in awe. For the first time, humans saw their cities shrink beneath them. These early aeronauts felt both wonder and fragility, suspended between earth and sky, with only thin fabric and fire holding them aloft. Balloons could rise, but they could not steer. The dream of controlled flight remained incomplete. Still, the boundary between imagination and reality had shifted forever. Throughout the 19th century, the quest for control guided every experiment. Engineers turned to gliders, studying the behavior of air across curved surfaces. Men like Otto Lilienthal in Germany spent years launching themselves from hillsides, measuring lift and drag with precision. His tragic death in 1896 during one such flight was not the end, but the threshold of progress. His meticulous records influenced two brothers in America who would soon change everything. Wilbur and Orville Wright studied Lilienthal's work and sought to solve what he could not: balance and control in powered flight. By the dawn of the 20th century, the foundations were set. The physics of air, the principles of lift, and the mechanics of control were converging. Humanity stood on the edge of a revolution not just in travel, but in perception itself. The sky was no longer unreachable. It was a field to be explored, measured, and mastered through understanding. The age of flight was about to begin, not as a myth reborn, but as science made real. Before powered flight dominated the imagination, humanity explored the skies through lighter-than-air craft, machines that rose without wings or engines, carried instead by the principles of buoyancy. Hot air balloons, first demonstrated in 1783 by the Montgolfier brothers in France, drifted upward by heating air within large fabric envelopes, creating a difference in density between the enclosed air and the atmosphere outside. Passengers, initially animals and then humans, experienced a serene ascent, gliding with the wind above towns and rivers, observing landscapes from an entirely new perspective. Balloons were fragile, their altitude controlled only by heat or ballast, yet they offered a first glimpse of sustained human presence in the sky and inspired generations to imagine flight as more than fleeting hops from elevated surfaces. As technology advanced, engineers sought greater control and capacity. Dirigibles, rigid or semi-rigid airships, added frames and propulsion systems to balloons, allowing them to navigate against the wind rather than drift aimlessly. In the early 20th century, Zeppelins in Germany, pioneered by Count Ferdinand von Zeppelin, demonstrated how massive airships could transport passengers, mail, and cargo across continents. Their envelopes contained hydrogen or helium to provide lift, while engines powered propellers that guided them with measured precision. These enormous vehicles, sometimes hundreds of meters in length, combined human ingenuity with engineering courage, carrying people through the sky in a manner both majestic and slow, allowing time for reflection on the beauty and scale of Earth below. The Hindenburg, completed in 1936, became the most famous of these rigid airships. Designed to cross the Atlantic with luxury and efficiency, it offered elegant cabins, dining halls, and observation decks suspended high above the ground. Its flight was quiet compared with contemporary airplanes, and passengers could observe clouds and coastlines with unobstructed views, feeling both the vastness of the sky and the gentle support of engineering below. Yet the Hindenburg also highlighted the limits and dangers of lighter-than-air technology. Its hydrogen lift, highly flammable, proved catastrophic in 1937 when disaster struck during landing. The accident marked the end of the airship era, demonstrating that even careful engineering must contend with the immutable laws of chemistry and physics. Despite the tragedy, airships and balloons left a legacy in both science and culture. They provided early studies of lift, pressure, and stability at scale. Pilots learned to navigate 3 dimensions with engines and rudders, translating theoretical principles into practical skill. The experience of observing wind currents, calculating ballast, and maintaining structural integrity informed later aviation pioneers who would move from lighter-than-aircraft to airplanes and eventually jets. Airships also captured public imagination, inspiring literature, art, and popular fascination with the sky as a navigable domain. In the quiet of reflection, one can imagine the slow rise of a balloon or the majestic glide of a zeppelin, suspended above the world in measured, controlled ascent. They were, in their way, the first machines to carry humanity not just into the air, but into a new perspective, preparing the mind for the powered flight that was soon to follow. In studying them, we see the careful application of physics, the observation of atmospheric behaviour, and the iterative experimentation that has always driven flight forward. Lighter-than-aircraft remind us that flight is not merely the act of moving through air, but the art of understanding it, respecting its forces, and designing machines that harmonise with them. Between the earliest gliders and the Wright brothers' first powered flights, a variety of experimental and transitional aircraft filled the skies, each exploring the boundaries of lift, control, and stability. Gliders, often constructed of wood and fabric, were launched from hillsides or towed behind vehicles, allowing pilots to study airflow, weight distribution, and control surfaces without the added complexity of engines. These machines, simple in appearance, were laboratories in motion, teaching the fundamental principles that would later underpin powered flight. At the same time, lighter-than aircraft continued to evolve. Semi-rigid and non-rigid airships, including observation balloons used in military contexts, demonstrated the practical uses of aerial platforms for surveillance and communication. Engineers experimented with envelope shapes, internal pressure, and propulsion mechanisms, gradually improving maneuverability and reliability. These developments provided lessons in structural engineering, material science, and atmospheric behavior that informed subsequent fixed-wing and rotary designs. Some inventors explored hybrid concepts, combining elements of gliders, kites, and balloons. Kite trains and ornithopters, machines that attempted to mimic bird-like flapping wings, offered limited success but stimulated thinking about control and thrust. Each failure and incremental improvement contributed to a growing body of empirical knowledge. Pilots learned how airflow responded to wing curvature, angle of attack, and surface tension, while engineers observed how materials performed under stress and strain. Experimental aircraft of this era also introduced early ideas of safety and redundancy. Pilots tested control surfaces that could adjust mid-flight, experimented with tail rudders for stability, and measured the effects of weight shifts on balance. These trials, often modest in scale, created a foundation for the more ambitious, powered machines that would soon dominate the skies. This period represents a bridge between imagination and mechanical reality. While the gliders and experimental airships did not yet carry passengers over long distances, they allowed humans to interact directly with the forces of flight, observing, measuring, and adjusting with each ascent and descent. In quiet reflection, one can trace a line from these tentative experiments to the precise calculations and powerful engines of later aircraft, recognizing that every controlled glide, balloon ascent, or kite lift brought humanity closer to mastering the air. The early years of the 20th century marked a quiet but decisive shift from dream to demonstration. On a cold December morning in 1903, at the windswept dunes of Kitty Hawk, North Carolina, the Wright brothers launched their fragile machine into the air for 12 sustained seconds. It was not the length of the flight that mattered, but the control within it. For the first time, a heavier-than-air machine lifted, balanced, and landed by its own power. Humanity had crossed an invisible boundary. What followed was not celebration so much as relentless refinement. The Wrights were engineers as much as inventors, and they knew their achievement was only a beginning. Their design relied on three essential controls: pitch, roll, and yaw. These corresponded to the three axes around which an aircraft moves. By warping their wings and adjusting a movable rudder, they achieved the coordinated motion required to stay stable in shifting air. This system, simple in concept yet revolutionary in effect, remains the basis for flight control today. The Wrights' understanding came from observation and experimentation rather than chance. They built a wind tunnel to test wing shapes, measuring lift and drag under controlled conditions. This approach marked the true start of aeronautical science, a movement from intuition to data. As their success became known, other pioneers began to experiment across Europe. In France, figures such as Alberto Santos Dumont and Louis Blériot developed lighter, more powerful machines. In 1909, Blériot crossed the English Channel in a monoplane of wood, linen and wire. His flight proved that aircraft could cover significant distance and navigate between points, not just hover over sand dunes. Each advance invited new challenges. Pilots confronted unpredictable weather, unreliable engines, and the constant threat of structural failure. To fly was still an act of courage and calculation in equal measure. Governments took notice. Within a decade, military and industrial interests recognized the potential of flight for reconnaissance, communication, and transport. Aircraft were no longer personal experiments, but strategic tools. The First World War became the first conflict shaped in the skies. Early aircraft carried cameras, later guns, and soon bombs. Design evolved rapidly under the pressure of necessity. Biplanes gave stability, but speed demanded streamlining. Engine power increased, materials improved, and aerodynamic theory advanced to match. Amid this transformation, a new profession emerged: the pilot. These early aviators were both scientists and explorers, learning to sense the motion of air through the vibrations of the machine. Their experiences filled the gaps left by incomplete equations. Through them, the science of flight gained not only precision but texture. They reported how air behaved at high altitudes, how control surfaces responded at different speeds, how turbulence felt through the controls. Data and human perception intertwined. By the end of the 1910s, aircraft had evolved from fragile gliders into robust machines capable of sustained travel. The world, once vast and separated by oceans and mountains, began to feel connected through the sky. The stage was set for aviation to move beyond war, beyond experiment, into the domain of commerce and exploration. The science was maturing, but its potential had only begun to unfold. Before the first powered flights, aviation was the domain of experimenters, tinkerers, and meticulous observers who studied the forces of lift, drag, and stability through repeated trials. Otto Lilienthal, in Germany during the 1890s, became a central figure in this period. He constructed a series of gliders and made controlled flights from hillsides, carefully documenting each experiment. Lilienthal's work emphasized the importance of understanding weight distribution, wing curvature, and angle of attack, principles that remain fundamental to aerodynamics today. His flights were graceful and measured, providing empirical evidence that heavier-than-air machines could be both controlled and repeatable. Other pioneers contributed in parallel. Percy Pilcher in England experimented with gliders that incorporated adjustable control surfaces, focusing on stability during descent. Samuel Langley in the United States, an astronomer and secretary of the Smithsonian Institution, approached flight through rigorous calculation and mechanical construction, building unmanned powered models that flew briefly before progressing to larger, more ambitious designs. These early attempts demonstrated the value of systematic observation and iterative improvement, showing that careful measurement could transform imaginative concepts into practical machines. Gliders of this era were laboratories in motion. Each ascent allowed observers to see how airflow interacted with wing shapes and surfaces, how control mechanisms responded, and how lift and drag could be balanced to maintain steady flight. Pilots learned to interpret subtle changes in wind and turbulence, gaining an intuitive understanding of aerodynamics that would later inform powered aircraft. Materials were simple but effective. Lightweight wood frames covered in fabric, ropes and wires providing tension and stability, creating structures that were both flexible and responsive. The iterative nature of these experiments cannot be overstated. Each flight built upon previous knowledge, correcting errors, refining design, and deepening understanding of air currents and lift generation. These pioneers faced danger at every turn. Controlled flight was fragile, and even small miscalculations could result in falls. Yet the lessons they gathered were invaluable. Lilienthal's detailed notebooks, sketches, and photographs became a guide for future engineers, including the Wright brothers, who would study them closely in developing their first powered, controlled airplane. Beyond mechanics, these early experiments instilled a sense of disciplined observation. Aviation was recognized as a science, not just a dream. By carefully documenting flights, measuring forces, and refining control methods, these pioneers created a foundation that transformed human flight from speculation into predictable, repeatable achievement. Their legacy is visible not only in the airplanes that would follow, but in the methodology of aviation itself. The combination of curiosity, calculation, and cautious experimentation. In reflecting on this period, one can imagine the quiet glide of a Lilienthal glider or the brief, tentative lift of Langley's models. The world below moves slowly as the air above is tested and measured. Every controlled descent, every small adjustment to a wing or tail, carries humanity a step closer to the mastery of the sky, bridging imagination with the laws of physics in a delicate, precise balance. While gliders and early powered aircraft dominated the imagination on land, water offered its own opportunities and challenges for flight. Seaplanes and amphibious aircraft emerged in the early 20th century, designed to take off and land on lakes, rivers, and coastal waters. These aircraft combined principles of aerodynamics with hydrodynamics, requiring careful attention to hull shapes, float design, and weight distribution to ensure stability both in the air and on water. Engineers studied how water resistance affected takeoff speed, how wave patterns influenced landing, and how to prevent structural fatigue from repeated contact with a liquid surface. Seaplanes played a vital role in exploration, connecting remote regions where runways did not yet exist. They carried mail across islands and coastal territories, enabling communication and commerce in areas previously accessible only by boat. Military forces quickly recognized their value. During World War I and the interwar years, seaplanes conducted reconnaissance, patrolled coastlines, and transported personnel to locations without established airfields. The ability to operate in both domains, air and water, made these aircraft versatile tools, blending the precision of flight with adaptability to natural environments. Early designs included single-float and twin-float configurations, each with distinct aerodynamic and hydrodynamic properties. Engineers balanced lift and thrust with buoyancy and drag, adjusting the angle of the hull, the placement of floats, and the wing configuration to ensure smooth transitions between water and air. Propeller placement was carefully considered to avoid spray damage, while lightweight, corrosion-resistant materials became essential for repeated exposure to moisture. Testing involved incremental trials, with pilots observing takeoff acceleration, handling during taxiing, and stability in crosswinds. By the 1920s and 1930s, larger flying boats like the Dornier d'Eau X and the consolidated Catalina demonstrated the scale and capability of seaplanes. They carried passengers, mail, and cargo over long distances, sometimes transoceanic, showcasing both endurance and reliability. Cabins were designed for comfort on extended flights, while hulls were reinforced to withstand the stress of repeated water landings. These machines bridged the gap between traditional aviation and global connectivity, offering lessons in structural engineering, power-to-weight ratios, and the interaction between air and water. Seaplanes and amphibious aircraft also influenced later developments in naval aviation and search and rescue operations. The knowledge gained from hull design, water handling, and variable load distribution informed both aircraft carriers and modern maritime helicopters. In quiet reflection, one can imagine a flying boat gliding onto a sunlit lake, engines humming softly, skimming the water before ascending into the sky. These aircraft remind us that aviation has always been defined not just by speed or altitude, but by adaptability, observation, and a careful understanding of the forces at work in every environment. The decade that followed the First World War opened a new era in which the airplane transformed from a tool of warfare into a vessel of connection. The The 1920s were defined by experimentation and optimism. Engineers refined the lessons learned in combat. Stronger engines, lighter materials, more reliable control systems, and began to apply them to civilian purposes. The sky was no longer only a battlefield or a testing ground, it was a network waiting to be charted. The notion of air travel as a public service took shape. Small postal routes became the earliest foundations of commercial aviation. Aircraft carried mail between cities faster than trains, crossing mountain ranges and deserts that once slowed communication. The United States Airmail Service, begun in 1918, demonstrated the practical reliability of flight. Pilots braved storms and darkness, guided at first by little more than landmarks and compass headings. Their routes would later form the backbone of passenger airlines. Innovation accelerated as designers sought efficiency and safety. The shift from wood and fabric to metal frames marked a turning point. Aluminum alloys offered strength without weight, allowing aircraft to grow larger and more aerodynamic. Monoplanes, single-wing designs, replaced the older biplanes as understanding of airflow improved. Streamlining became an art guided by science. The rounded fuselage and tapered wings of the 1930s represented both elegance and function, reducing drag and increasing lift. It was also an age of daring feats that captured the public imagination. In 1927, Charles Lindbergh flew solo across the Atlantic, linking New York and Paris in 33 hours. His flight demonstrated not just endurance, but the reliability of long-distance flight under human control. Amelia Earhart's journeys soon followed, expanding the narrative to include both exploration and equality. Each flight was both a test of technology and a study in the human relationship with isolation, weather, and the unknown. Behind these achievements lay the deepening science of aerodynamics. Wind tunnels became essential tools in laboratories across the world. Engineers measured the behavior of air at different angles and speeds, refining the understanding of lift and drag into precise equations. The development of airfoils, wing shapes that balance pressure differences, became central to aircraft design. Lift was no longer a mystery of motion, but a predictable result of geometry and flow. Propellers too were studied as rotating wings, each blade an airfoil designed to convert engine power into thrust with maximal efficiency. By the late 1930s, aircraft had reached a new level of performance. Multi-engine planes carried passengers across continents and oceans. Pressurized cabins allowed flight at higher altitudes, where thinner air meant less resistance and smoother travel. The science of meteorology began to integrate with aviation, improving navigation and safety. Flight had evolved from a mechanical experiment into a coordinated system of knowledge, skill, and infrastructure. What had begun with gliders on hillsides now connected cities and nations. The dream of flight had become a routine, yet it remained a source of quiet wonder. Every ascent into the sky echoed the ancient wish to see the world from above, now realized through precision, mathematics, and steady human progress. The next step would be faster, higher, and more powerful than ever imagined. While fixed-wing aircraft advanced steadily between the wars, another branch of aviation quietly developed: rotorcraft. Unlike airplanes, helicopters and autogyros generate lift through spinning blades, allowing vertical takeoff, hovering, and precise maneuvering in 3 dimensions. Early experiments in rotary wing flight date back to the 1920s and 1930s, when inventors explored the possibilities of lift generated by rotating airfoils rather than fixed wings. Autogyros, developed by Juan de la Cierva, relied on an unpowered rotor to create lift while a conventional engine and propeller provided forward thrust. These machines demonstrated the potential for vertical lift and low-speed control, opening pathways that fixed-wing aircraft could not access. The first practical helicopters emerged in the 1930s and 1940s. Pioneers such as Igor Sikorsky in the United States refined the design of a single main rotor with a tail rotor to counteract torque, solving a critical stability problem. His VS-300 prototype became a template for modern helicopters, demonstrating controlled vertical takeoff, hovering, and lateral flight. These machines were complex, requiring careful attention to aerodynamics, rotor mechanics, and engine power. Engineers learned to balance lift, thrust, and torque dynamically, while pilots developed the skill to manage cyclic and collective controls simultaneously. Helicopters offered capabilities that fixed-wing aircraft could not match. They could access remote areas, land on uneven terrain, and provide rapid vertical mobility. During World War II, experimental rotary wing craft were used for observation, rescue, and transport, while in the post-war period, helicopters found roles in civilian industries, including search and rescue, firefighting, medical evacuation, and urban transport. Their slow, hovering flight allowed close observation of landscapes, precise delivery of cargo, and flexible movement in congested environments. The science of rotary flight differs in key ways from fixed-wing aerodynamics. Lift is generated by the rotor blade's motion through air, but as speed and angle change, airflow patterns, vortex formation, and torque effects must be managed in real time. Engineers develop tail rotors, coaxial rotors, and tiltrotor designs to address these challenges. Advanced materials, lightweight engines, and precision engineering gradually improved efficiency and reliability, making helicopters practical for a wide range of missions. Today, helicopters represent a mature branch of aviation, yet they retain a sense of intimacy with the air. Pilots can hover silently above the ground, ascend through turbulence, and descend with precision that fixed-wing aircraft cannot achieve. They are living examples of human ingenuity in mastering three-dimensional flight, expanding the applications of aerodynamics, and complementing the history of airplanes with vertical mobility. The rotorcraft story bridges experimental aeronautics with practical utility, reminding us that the sky accommodates more than speed and distance. It also allows careful, deliberate control over every dimension of motion. Throughout the early decades of aviation, women played a crucial role in expanding both the technical and cultural boundaries of flight. Figures such as Amelia Earhart, Bessie Coleman, and Jacqueline Cochran demonstrated that mastery of the skies was not limited by gender, while contributing to advances in piloting, navigation, and public engagement. Amelia Earhart, famous for her transatlantic solo flight in 1932, exemplified the blend of courage and precision that defined early long-distance aviation. Her careful planning, attention to meteorology, and skillful management of fuel and weight distribution underscored the importance of meticulous preparation in flight. Bessie Coleman, the first African-American woman to earn a pilot's license, overcame social and systemic barriers to achieve proficiency in European flight schools. Her work inspired generations of pilots, demonstrating that determination and understanding of aerodynamics, lift and control could overcome obstacles both in the air and on the ground. Jacqueline Cochran contributed significantly to both aviation performance and organisation. She set multiple speed and altitude records and played a central role in organising the Women Air Force Service pilots during World War II, ensuring that aviation skills contributed to broader operational needs. Women in aviation not only broke social conventions, but also advanced technical knowledge. Their flights tested aircraft performance under different conditions, refined navigation techniques, and demonstrated endurance and reliability. Many participated in long-distance and record-setting flights, requiring mastery of wind currents, fuel efficiency, and mechanical systems. By documenting their observations, adjusting control techniques, and training new pilots, these women extended the practical understanding of flight mechanics while inspiring broader participation in aviation. Cultural impact accompanied technical achievement. Public interest in female pilots elevated awareness of aviation and encouraged support for infrastructure, schools, and technological research. Media coverage of long-distance flights, air shows, and endurance competitions popularized the principles of flight: lift, thrust, drag, and weight in ways accessible to a wide audience. This blend of technical demonstration and social influence created a bridge between experimental flight and its normalization as both transportation and sport. Reflecting on this era, one can imagine the quiet concentration in a cockpit, hands steady on the controls, eyes scanning instruments and sky, as a pioneering female pilot maneuvers over oceans, deserts, or mountains. Their work illustrates that aviation is both a technical and human endeavour, reliant not only on engines and wings, but on observation, calculation, and courage. By integrating meticulous scientific practice with exploration, these women helped shape the trajectory of flight, demonstrating that mastery of the air is achieved through knowledge, skill, and a disciplined respect for the forces that govern it. The 1940s carried aviation into an age of rapid and often turbulent transformation. The Second World War demanded advances in aircraft design at a pace unmatched in history. What began as a field defined by incremental progress became one of urgency and invention. Aerodynamics, propulsion, and material science converged under the pressure of necessity. Every aspect of flight was tested, measured, and refined. The result was a leap forward that reshaped both the science and the meaning of aviation. Military aircraft evolved from the slow biplanes of earlier decades into sleek, high-speed monoplanes. Aluminum replaced wood entirely. Riveted skins formed aerodynamic shells capable of withstanding great stress. Engineers understood that drag was the enemy of speed and that weight must be reduced wherever possible. Propulsion systems advanced alongside airframes. Supercharged piston engines delivered greater power at altitude, while propeller design optimized thrust through efficiency of rotation. Aircraft such as the British Spitfire, the American P-51 Mustang, and the German Messerschmitt Bf 109 represented the peak of piston-driven technology. The war also accelerated the development of navigation and instrumentation. Pilots relied on radio beacons, gyroscopic compasses, and newly standardized cockpit layouts that improved coordination and safety. Radar, born from radio research, revolutionized detection and control. It allowed aircraft to operate in darkness and through cloud, linking physics and defense in a way that permanently changed aviation's capabilities. Yet the most profound change came with the introduction of jet propulsion. In 1939, the German Heinkelhaie 178 became the first aircraft powered by a turbojet engine to fly. The principle was simple but transformative. Instead of spinning a propeller to pull an aircraft forward, the jet expelled high-velocity exhaust to push it through the air. This new form of thrust promised far higher speeds and altitudes. The British Gloucester Meteor and the German Messerschmitt Me 262 became the first operational jet fighters, marking the dawn of a new aerodynamic regime. The familiar limits of propeller-driven flight had been broken. At the same time, large transport aircraft became essential to logistics. The Douglas C-47 and Boeing B-17 carried troops, supplies, and equipment across continents. Long-range navigation methods such as celestial fixes and radio triangulation became standard practice. The coordination of thousands of aircraft, each following complex routes, led to the early structures of global air traffic control. When the war ended, the scientific groundwork for a new kind of aviation was already in place. Jet engines promised faster travel, radar allowed safer navigation, and the knowledge of high-speed aerodynamics opened the path towards supersonic research. The post-war years would see this technology redirected from combat to connection, from destruction to exploration. The same principles that had enabled machines of war would soon carry passengers between continents and eventually propel humanity toward the edge of space. The 1940s closed with the sound of jet engines replacing the thrum of propellers. The air had changed. The science of flight, once devoted to lifting off the ground, was now focused on mastering speed itself. The mid-20th century saw a dramatic shift in aviation as engineers pursued speed and altitude beyond anything previously achieved. Experimental aircraft, collectively known as X-planes, became laboratories in the sky, exploring supersonic and hypersonic flight. The Bell X-1, piloted by Chuck Yeager in 1947, broke the sound barrier, demonstrating that controlled supersonic flight was possible despite previous assumptions about a sound barrier as a natural limit. Engineers studied shock waves, compressibility of air, and the behavior of control surfaces under supersonic conditions, applying fluid dynamics in ways that had been purely theoretical before. Following the X-1, the Bell X-15 program pushed the envelope even further. This rocket-powered aircraft reached altitudes above 100 kilometers and speeds exceeding Mach 6. The X-15 provided critical data on aerodynamic heating, structural stress, and high-altitude flight behavior, directly informing both aircraft and spacecraft design. Pilots needed specialized training to manage both atmospheric flight and near-space conditions, bridging aerodynamics and astronautics in practical application. Instruments monitored air pressure, temperature, and structural loads, allowing engineers to analyze every phase of flight with unprecedented precision. Supersonic and hypersonic flight introduced unique challenges. Shock waves caused intense vibrations, control surfaces became less effective at high speed, and air friction generated extreme heat, requiring advanced alloys and heat-resistant coatings. Engineers developed new theories of airflow, boundary layers, and thermal expansion, translating them into practical solutions such as swept wings, thin fuselages, and reinforced leading edges. Each flight was both a scientific experiment and a validation of mathematical predictions, testing the limits of materials, propulsion, and human endurance. These experimental aircraft were not only technological achievements, but cultural milestones. They captured the imagination of the public, symbolizing a new era in which humanity could move faster than sound and venture toward the edge of space. The lessons learned informed both military and commercial aviation, shaping designs for supersonic fighters, reconnaissance aircraft, and the first concepts of supersonic passenger travel. In reflecting on this period, one can imagine the X-planes climbing through the sky, engines roaring, the horizon distorting as sound and speed converge. Each flight demonstrates the meticulous application of physics, the courage of pilots, and the relentless pursuit of knowledge. The experimentation of the X-plane era illustrates that aviation is not static. It evolves continuously as humanity measures, tests, and expands the limits of what air can support. The Cold War era transformed aviation into both a scientific and strategic endeavor, where speed, altitude, and stealth became central to national security. Aircraft such as the Lockheed U-2 and the SR-71 Blackbird exemplified the extremes of reconnaissance and high-performance flight. The U-2, first flown in the 1950s, could reach altitudes above 70,000 feet, carrying cameras and sensors to gather intelligence while remaining largely beyond the reach of enemy aircraft. Its long, slender wings and lightweight structure maximized lift in thin air, demonstrating careful application of aerodynamics to operational needs. The SR-71, developed in the 1960s, pushed both speed and altitude further, routinely exceeding Mach 3 while operating above 80,000 feet. Its design reflected meticulous attention to material science, with titanium alloys used extensively to withstand the intense heat generated by air friction at high speed. Every surface was shaped to reduce radar visibility, introducing concepts that would evolve into stealth technology. Engineers studied thermal expansion, structural stress, and aerodynamics at extreme velocities, creating an aircraft that was simultaneously fast, high, and survivable. Stealth technology, first applied more broadly in later decades, combined geometry, coatings, and materials to reduce radar cross-section. Aircraft were designed not just to move efficiently through air, but to minimize detection, integrating physics, engineering, and electronic sensing into a single coherent system. These innovations required precise calculation of angles, surfaces, and absorption materials, illustrating that the science of aviation had expanded from lift and propulsion to include invisibility and control in a digital and radar-mediated environment. During this era, aviation also extended into unmanned systems. Early drones and reconnaissance UAVs supplemented manned aircraft, demonstrating that flight could be both autonomous and mission-specific. Sensors and telemetry allowed remote operation, providing intelligence without risk to human pilots. These systems laid the foundation for modern autonomous aircraft, integrating robotics, navigation, and aerodynamics in ways that foreshadowed 21st century developments. Reflecting on the Cold War period, one can picture the U-2 gliding silently over distant territory, or the SR-71 streaking across the sky, leaving vapor trails in its wake. These aircraft were exercises in precision, calculation, and strategic foresight, showing that flight was not only about movement or exploration, but about mastery of conditions, materials, and information. The era demonstrated that the evolution of aviation is continuous, with each generation of machines building on previous knowledge to push the boundaries of speed, altitude, and capability, while maintaining the delicate balance of forces that allows humans and machines to remain aloft. When peace returned in the late 1940s, aviation entered its first true age of expansion. The war had created not only advanced machines, but also a generation of engineers, pilots, and mechanics who understood them. Military technology now sought civilian purpose. The same jet engines that once powered fighters began to promise fast, high-altitude travel for ordinary passengers. The groundwork for the modern airline industry was forming from the remnants of war. Manufacturers turned quickly to redesign military aircraft for peacetime. The Douglas DC-4 and Lockheed Constellation brought long-distance air travel to the public. These piston-driven airliners linked continents with unprecedented reliability, flying above most weather and offering steady comfort that earlier aircraft lacked. Pressurization systems maintained breathable cabin air as planes climbed into thinner atmosphere. This single innovation changed the human experience of flight, allowing smooth, quiet journeys high above the turbulence of the lower sky. Jet propulsion soon followed. In 1952, the British de Havilland Comet became the world's first commercial jet airliner. It represented the fusion of aerodynamics, metallurgy, and engineering precision. The Comet flew faster and higher than any passenger aircraft before it, reducing intercontinental travel times from days to hours. Early models suffered structural failures as pressurization cycles revealed weaknesses in the metal fuselage, but the lessons learned were invaluable. Engineers studied fatigue, stress concentration, and the properties of aluminum under repeated strain. From those findings, safer and stronger designs emerged. The 1950s became a decade of rapid scientific maturation. Jet engines evolved into more efficient turbofans, combining thrust with lower fuel consumption and noise. Aerodynamic shapes grew sleeker, guided by new wind tunnel studies and early computational models. The Boeing 707 and Douglas DC-8, both introduced before the decade's end, ushered in the jet age proper. They carried hundreds of passengers across oceans at speeds exceeding 900 kilometers per hour. The world began to feel smaller, its distances redefined by altitude and velocity. Aviation infrastructure expanded to match this growth. Runways lengthened to handle faster aircraft, air traffic control adopted radar guidance as standard, and meteorology integrated satellite observation. The science of flight was no longer limited to the aircraft itself, but encompassed an entire ecosystem: navigation, communication, maintenance, and human physiology. Long-haul flight introduced new studies into fatigue, circadian rhythm, and oxygenation, linking aeronautics with medicine. Public perception of flying also changed. What had once been dangerous and extraordinary became part of daily life for business, diplomacy, and tourism. Passengers could cross oceans in daylight, dine above cloud layers, and arrive in another hemisphere before nightfall. The technical marvel became routine, yet beneath the calm surface of commercial flight lay a constant current of refinement and control. Every component, from wing to rivet, was shaped by lessons learned in the laboratory and in the air. By the close of the 1950s, humanity had not only mastered powered flight, but had made it practical, predictable, and global. The jet age had begun, and the sky was no longer a frontier, it was a highway. But at its edges, a new question had already formed. If flight could conquer the atmosphere, could it also reach beyond it? As aviation progressed through the mid and late 20th century, engineers and pilots began exploring ways to transcend conventional limitations of speed, altitude, and operational environment. This exploration led to vertical takeoff and landing aircraft, spaceplane concepts, and advanced propulsion experiments, technologies that would expand the definition of flight and integrate it more closely with space exploration. Vertical lift allowed aircraft to take off and land in confined areas without long runways, opening urban air mobility and military flexibility, while experimental propulsion challenged engineers to reconsider how energy could be converted into thrust under extreme conditions. One of the earliest practical VTOL designs was the Hawker Siddeley Harrier, developed in the 1960s. Its vectored thrust engine allowed the aircraft to rise vertically, hover, and transition seamlessly into forward flight. This capability depended on precise balance between engine power, nozzle orientation, and aerodynamic surfaces. Engineers analysed airflow not only around wings, but also around the fuselage and exhaust, studying how jet wash interacted with the surrounding air and surfaces. The Harrier illustrated that mastery of the air was not solely about wings and forward motion, but about the dynamic control of forces in multiple directions simultaneously. Pilots required exceptional skill to manage collective thrust and directional stability, while engineers worked to design engines and control systems that could respond instantly to changing conditions. Simultaneously, experimental aircraft programs pushed the boundaries of speed and altitude, building a bridge towards spaceflight. Lifting body research conducted in the United States during the 1960s and 1970s sought to understand how a fuselage alone could generate lift without traditional wings. These craft, including the X-24 and HL-10, demonstrated controlled re-entry from high-altitude flight, providing critical data for the design of the space shuttle and other reusable spacecraft. Pilots and engineers studied the balance between lift, drag, and stability at speeds far beyond conventional flight, refining materials, control surfaces, and navigation systems to withstand extreme temperatures, low atmospheric density, and high aerodynamic stress. Propulsion systems also evolved to meet these new challenges. Ramjets and scramjets, designed to operate efficiently at supersonic and hypersonic speeds, relied on the compression of incoming air at high velocity to generate thrust, eliminating the need for complex moving parts found in traditional turbines. These engines required precise engineering of intake geometry, fuel injection, and thermal management to maintain stability and prevent catastrophic failure. Experimental flights tested these systems in controlled environments, gradually expanding the operational envelope of high-speed flight. While most programs remained experimental, the knowledge gained influenced later designs for reconnaissance aircraft, missile systems, and proposed commercial supersonic transport. Energy management became a critical component of modern aviation. Electric and hybrid electric propulsion systems entered development to address environmental and operational limitations. Engineers studied battery energy density, thermal management, and weight distribution to enable vertical and horizontal flight while maintaining efficiency. Early prototypes demonstrated that distributed electric propulsion could enhance stability, reduce noise, and improve responsiveness in complex urban environments. Combined with lightweight materials and optimized aerodynamics, these aircraft represented a new paradigm. Flight achieved not only through mechanical power, but through integrated systems of sensors, software, and adaptive control. Spaceplanes, representing the fusion of aviation and astronautics, exemplify this evolution. Vehicles such as the X-15, lifting bodies, and more recent reusable spacecraft demonstrated that principles of flight remain consistent across extreme conditions, yet operational demands increase exponentially. Lift, drag, and thrust must be balanced under varying atmospheric density, gravity, and thermal stress. Pilots and engineers collaborated to develop flight envelopes, emergency procedures, and navigation techniques that could function both in the atmosphere and near space. These systems integrated advanced telemetry, sensors, and real-time data analysis to ensure safety and reliability in conditions that few humans had previously encountered. Urban air mobility, once theoretical, began emerging as a practical extension of these technologies. Electric vertical takeoff and landing vehicles, or eVTOLs, combine lessons from helicopters, fixed-wing aerodynamics, and distributed propulsion. Small, quiet, and precise, these craft can carry passengers short distances in urban or remote environments, reducing congestion and opening new operational possibilities. Designers balance lift, stability, rotor aerodynamics, and battery efficiency, ensuring that safety and predictability remain paramount. Each prototype flight provides further empirical data, refining control algorithms and energy management systems. Beyond mechanical and aerodynamic development, the late 20th and early 21st centuries emphasized systems integration. Aircraft became nodes in a networked environment where navigation, communication, and automation intersect. Real-time flight data is monitored, processed, and adjusted, allowing the machine to respond to turbulence, air traffic, and environmental factors automatically. Pilots maintain supervision, interpret complex data, and intervene when necessary, but much of the continuous optimization occurs through software and sensor networks. This integration extends to UAVs, autonomous cargo vehicles, and hybrid human-machine systems, representing a new horizon in aviation where intelligence and physics collaborate. Environmental considerations also shape design priorities. Engineers refined engines to minimize emissions, reduce noise, and improve energy efficiency. Materials science contributed to lighter, stronger airframes, while sustainable aviation fuels and hybrid electric systems reduced the carbon footprint of both vertical and horizontal flight. The interplay of environmental science, physics, and engineering illustrates that modern aviation is as much about stewardship as it is about performance. Flight must be efficient not only in energy, but in its impact on the world it traverses. Reflecting on these advances, one can imagine a quiet, hovering eVTOL ascending above a city at dawn, a sleek spaceplane gliding at the edge of the atmosphere, and a Harrier transitioning from vertical lift to forward motion with precision. Each represents a continuum of human inquiry, experimentation, and mastery of the forces that govern air and energy. The science of lift, drag, thrust, and weight remains foundational, yet it is applied with increasing sophistication, integrated with propulsion innovation, environmental awareness, and autonomous control. This era of aviation demonstrates that mastery of the sky is not a static achievement, but a continuous process. Each technological advance builds upon centuries of observation, experimentation, and refinement, from balloons and gliders to supersonic aircraft, helicopters, and spaceplanes. The balance of forces, careful calculation, and respect for the laws of physics remain constant, while the methods and materials evolve. Flight has become a multi-dimensional endeavour, encompassing vertical and horizontal mobility, subsonic and supersonic speeds, and even atmospheric to space transitions. In this, aviation stands as both a scientific pursuit and a quiet, continuous art, carrying humanity forward with precision, curiosity, and respect for the invisible forces that sustain it. The 1960s opened with the sound of jet engines rising across the world and ended with rockets piercing the atmosphere. It was a decade when the limits of flight expanded into the silence of space. Aircraft design reached new levels of precision, and the science that had once studied lift and drag began to merge with the physics of orbital motion. The sky was no longer an endpoint, but a bridge between Earth and the void beyond. Commercial aviation reached maturity during this period. The Boeing 707 and Douglas DC-8 dominated global routes, their reliability making intercontinental flight a normal part of business and leisure. Airlines refined cabin environments, pressurization, and jet maintenance into standardized systems. Air traffic control adopted radar coordination on an international scale, linking ground stations with airborne transponders to track thousands of aircraft in real time. The act of flying had become both ordinary and deeply technical, guided by invisible networks of physics, communication, and human attention. Meanwhile, engineers sought new frontiers in speed. The development of supersonic flight represented the next great step. Breaking the sound barrier required confronting forces unknown at subsonic speeds. Shock waves, compressibility effects, and extreme aerodynamic heating. In 1947, the Bell X-1 had been the first to exceed Mach 1 under rocket power, but it was in the 1960s that sustained supersonic flight became practical. Research aircraft such as the North American X-15 explored the high atmosphere at speeds exceeding Mach 6, gathering data crucial for both aviation and space exploration. The decade also saw the emergence of commercial supersonic design. The Anglo-French Concorde and the Soviet Tu-144 aimed to connect distant cities in half the usual time. Their needle-like shapes and delta wings reflected years of aerodynamic study. The Concorde, introduced later in the 1970s, would become a symbol of elegance and precision, but its origins were deeply rooted in the experimental fervour of the 1960s. Engineers were learning not only how to fly faster, but how to manage the immense thermal and structural stresses that such flight imposed. Parallel to these developments, aviation science fed directly into the space race. Rocket propulsion, high-altitude flight suits, and pressurized cabins all evolved from aeronautical principles. NASA's Mercury, Gemini, and Apollo programs extended these lessons upward. The same equations that governed airflow around a wing also described re-entry heating and orbital drag. Many of the test pilots who flew experimental aircraft transitioned into astronauts, carrying the methods of aeronautical engineering into the realm of astronautics. On Earth, passenger flight became an emblem of progress. Jetliners carried the world's leaders, goods and cultures between continents with mechanical regularity. Airports expanded into cities within cities, complete with control towers, radar domes, and maintenance hangars. The infrastructure of global travel had crystallized. By the end of the 1960s, flight had evolved from the delicate balance of fabric and wire into a synthesis of high-temperature alloys, pressurized systems, and computer-assisted navigation. The principles of aerodynamics remained the same, but their application now reached beyond the atmosphere. The science of aircraft had led humanity to the threshold of space, and the air itself was no longer the final medium of flight. It was only the beginning. The 1970s marked the era when aviation grew from innovation into infrastructure. The science of flight had stabilized, and the focus shifted towards scale, efficiency, and reliability. Jet propulsion was no longer experimental, it was the standard. Aircraft became larger, safer, and more capable of carrying both people and commerce across the planet. The dream of global air travel had matured into an organized system of movement that linked nearly every major city on Earth. At the center of this transformation was the introduction of the wide-body airliner. Boeing's 747, first flown in 1969, defined the decade. With its double-decked cockpit and capacity for hundreds of passengers, it represented a new kind of engineering challenge: how to maintain aerodynamic performance and structural integrity at unprecedented size and weight. The 747's design relied on advanced materials and computational modeling that allowed engineers to predict stress and fatigue across its frame. Its 4 high-bypass turbofan engines provided the thrust necessary to lift its massive form efficiently through the stratosphere. The result was a machine that reshaped both physics and economics, making long-distance air travel accessible to the public on a scale never seen before. Airports expanded to handle the new giants of the sky. Runways lengthened, terminals grew, and automated systems were introduced for navigation and scheduling. The science of flight extended beyond the aircraft into the realm of air traffic management and meteorological forecasting. Precision radar, satellite communication, and standardized flight paths formed an invisible web of coordination that kept thousands of aircraft safely separated as they crossed oceans and continents. During the same decade, environmental awareness began to influence aeronautical research. Engineers studied the relationship between jet exhaust, atmospheric chemistry, and noise pollution. The high-bypass turbofan emerged as both a technical and environmental improvement. reducing fuel consumption and sound output while maintaining thrust. Aerodynamics was refined further through computer simulations that replaced some of the need for costly wind tunnel experiments. Airflow patterns could now be visualized digitally, allowing optimization of wing shapes and control surfaces before a single prototype was built. The 1970s also saw the rise of avionics, the integration of electronics into flight control and navigation. Early analog systems gave way to digital instrumentation, which improved accuracy and reduced pilot workload. Automatic flight control, inertial navigation, and weather radar made long-distance flight more predictable and safe. The cockpit became an evolving interface between human and machine, reflecting both engineering precision and the growing importance of information management in flight. Beyond commercial aviation, military research continued to push the boundaries of performance. Stealth technology began to take form, driven by the physics of radar reflection and the absorption of electromagnetic waves. The first concepts of low observable design were studied not for speed, but for invisibility. These studies marked the emergence of a new dimension of aerodynamics, one concerned not only with the movement of air, but with the behavior of energy across surfaces. By the close of the 1970s, flight had become an integral part of civilization's structure. Aircraft connected economies, families, and ideas. The science that once sought to understand how to lift a machine from the ground now managed a complex global system that rarely slept. The challenge was no longer whether humanity could fly, but how it could do so farther, quieter, and more efficiently in a world that had come to depend on the rhythm of the skies. The 1980s brought refinement rather than revolution. The essential principles of flight were mastered, but the application of those principles grew sharper through computing, materials science, and automation. Aircraft became more intelligent, more efficient, and more integrated into global systems. Aviation was no longer simply about movement through the air, it was about managing complexity at scale. Digital technology entered the cockpit in full. The shift from analog gauges to electronic flight instrument systems, known as glass cockpits, transformed the way pilots interacted with their machines. Multifunction displays replaced clusters of dials, consolidating flight data into clean dynamic visualizations. Computers could process sensor inputs faster than any human, reducing error and improving response to environmental conditions. Fly-by-wire control systems, first implemented on aircraft like the Airbus A320, translated pilot commands into electrical signals that adjusted control surfaces with precision and built-in safeguards. This advancement marked a philosophical shift. The aircraft itself became an active participant in maintaining stability and safety. Aerodynamics reached a mature form, but subtle advances continued. Winglets, vertical tips at the ends of wings, were introduced to reduce induced drag, improving fuel efficiency without major redesign. Computational fluid dynamics, enabled by increasing computer power, allowed engineers to model airflow in 3 dimensions and test thousands of virtual variations before physical production. The result was smoother, quieter, and more fuel-efficient aircraft across both commercial and military fields. Composite materials entered wide use. Carbon fiber and advanced polymers replaced portions of aluminum structures, combining strength with lightness. These materials resisted corrosion and fatigue, allowing longer aircraft lifespans with reduced maintenance. The science of metallurgy expanded into the chemistry of bonding and molecular structure, blending physics with materials engineering. Every kilogram saved meant less fuel burned and greater range achieved, a metric that defined efficiency in both economic and environmental terms. Commercial air travel in the 1980s became a universal mode of connection. Airlines standardized fleets, global alliances formed, and scheduling systems synchronized across continents through digital communication networks. Satellites provided global positioning, replacing earlier methods of navigation that relied on ground-based beacons. The precision of flight paths improved by orders of magnitude, allowing dense but safe skies above the busiest routes. In military and research aviation, new forms emerged. Stealth aircraft such as the F-117 Nighthawk demonstrated the practical outcome of radar-absorbing design principles first studied in the previous decade. Their angular surfaces and specialized coatings made them nearly invisible to radar detection, turning geometry itself into a defensive tool. High-performance aircraft pushed materials to their limits, with titanium alloys and heat-resistant composites enabling sustained supersonic speeds. By the end of the decade, the combination of digital control, new materials, and computational modeling had redefined what it meant to design and operate an aircraft. Flight had become a closed-loop system of sensors, processors, and feedback. The human pilot remained essential, but now shared control with machines designed to think in milliseconds. Aviation's progress was no longer defined only by altitude or speed, but by precision, the ability to sustain perfect balance between lift, thrust, and intelligence. The world below continued to shrink as aircraft above became smarter, safer, and more efficient. Flight had evolved into a seamless interaction between human intent and algorithmic control, carried out through the invisible mathematics of the air. The 1990s continued the quiet evolution of flight, where progress emerged less from new forms than from the steady refinement of technology. Computers, satellites, and advanced materials defined the era. Air travel became routine on a global scale, supported by a network of systems so vast and synchronized that its complexity was almost invisible. The science of aircraft shifted from invention to optimization, from conquering the air to mastering every variable within it. Fly-by-wire control systems became the standard in both commercial and military aircraft. Pilots no longer moved control surfaces directly, but issued commands interpreted through layers of software that calculated the safest and most efficient response. This allowed engineers to design inherently unstable aircraft that computers could stabilize instantly, giving greater maneuverability and performance. The Airbus A320 and Boeing 777 embodied this philosophy. Machines built not just to fly, but to think. Navigation entered a new phase through the global positioning system. Satellite signals replaced radio beacons and celestial fixes, providing precise positional data anywhere on Earth. This development linked aerospace engineering with orbital mechanics, merging aviation and space technology in practical form. Air routes became more accurate, fuel usage more predictable, and scheduling more reliable. The invisible infrastructure above Earth now guided every flight below it. Aerodynamics reached its most efficient equilibrium. Winglets became common across commercial fleets. Fuselages were refined for smoother laminar flow, and engines achieved higher bypass ratios for quieter, more economical performance. The turbofan, perfected over decades, had reached near optimal efficiency for subsonic travel. Engineers began to explore alternative fuels and noise reduction, anticipating the environmental concerns that would soon dominate the industry. Inside the aircraft, automation deepened. Autopilot systems could manage entire phases of flight under supervision, from climb to descent. Digital flight management computers calculated optimal paths based on weather, weight, and wind conditions. The pilot's role evolved from direct control to system oversight, interpreting data rather than constantly manipulating controls. The human-machine partnership had matured into mutual dependence, each compensating for the other's limitations. The 1990s also introduced greater standardization across international aviation. Safety protocols, maintenance procedures, and air traffic regulations were harmonized through global organizations such as ICAO and IATA. These frameworks relied on precise data exchange and shared understanding of physics, engineering, and human factors. The result was the safest period in the history of flight, built upon mathematics, discipline, and the quiet rigor of systems thinking. In parallel, military aviation explored stealth and sensor fusion. The B-2 Spirit demonstrated near-invisible radar profiles, while new avionics integrated radar, infrared, and satellite data into unified displays. Every sensor became part of a collective awareness, a digital extension of perception. The line between pilot and system blurred further, guided by algorithms that anticipated rather than merely responded. By the end of the decade, flight had achieved a state of calm mastery. The roar of early engines had softened into the low hum of efficiency. The equations of lift, drag, and thrust had been solved and refined into daily practice. Air travel no longer astonished, it reassured, sustained by constant calculation. The dream of flight had become infrastructure, embedded in the rhythm of modern civilization. The early 2000s brought aviation into the digital century. The physical principles of flight remained unchanged, but the systems that governed it became fully networked. Every aircraft was now a node in a global information web, tracked, analysed, and managed through streams of data transmitted between air, ground, and satellite. The sky had become transparent to technology, mapped in real time by algorithms and sensors that work together with quiet precision. Airliners introduced new levels of automation and integration. The Boeing 777 and Airbus A330 families represented the synthesis of decades of engineering refinement. Their fly-by-wire systems operated through redundant computers, each capable of taking over if another failed. Electronic checklists, digital diagnostics, and satellite link communication transformed the cockpit into a data hub. The aircraft continuously reported its own condition, engine performance, fuel balance, and even predictive maintenance indicators. The science of flight had evolved into the science of systems reliability. Materials continued to advance. The growing use of carbon fiber reinforced polymers allowed lighter, stronger structures with greater resistance to fatigue. This transition reached its height later in the decade with the Boeing 787 Dreamliner and Airbus A350, whose composite airframes reduced weight and improved fuel efficiency by over 20% compared to earlier models. The chemistry of polymers joined aerodynamics and propulsion as a core field of aviation science. Navigation became fully satellite-based. GPS precision reached within meters, enabling aircraft to follow narrow corridors across the globe with minimal deviation. Air traffic control adapted by implementing required navigation performance procedures, allowing more aircraft to share airspace safely. Automated Dependent Surveillance Broadcasts, ADS-B, enabled planes to transmit their exact position to others nearby, turning the sky into a cooperative network of awareness. Security concerns following the events of 2001 reshaped the experience of flight. Airports became controlled environments of screening and protocol. Aviation safety expanded beyond mechanical reliability to include human and procedural defense. The balance between freedom and protection became a defining feature of early 21st century air travel. Environmental considerations also began to shape design priorities. Jet engines were refined to reduce emissions and noise, and studies intensified into alternative fuels such as biofuel blends and synthetic kerosenes. The science of flight was no longer focused solely on performance, but on sustainability, on how to preserve the efficiency of the system without exhausting the planet that sustained it. By the end of the decade, aviation had achieved a state of near-perfect reliability. Mechanical failures were rare, accidents rarer still, and air travel had become statistically one of the safest activities in daily life. The human role continued to shift towards supervision and decision-making within complex automated systems. The machine, once a tool, had become an intelligent partner, its sensors and processors forming a distributed consciousness that never slept. The 2000s closed with flight defined not by the boundaries it broke, but by the systems it maintained. The miracle of lift had become invisible, embedded in circuits, software, and seamless motion. The airplane was now a synthesis of physics and information, an elegant, self-monitoring structure that carried humanity through the air with measured certainty. The 2010s were the decade when aviation entered full digital maturity. The airplane became both a vehicle and a data platform, part of a global network of sensors, algorithms, and communications that spanned the atmosphere. Flight was no longer just movement through air. It was the continuous exchange of information between aircraft, satellites, and the systems that governed them. Composite airframes, pioneered in the previous decade, became standard for new designs. The Boeing 787 Dreamliner and Airbus A350 exemplified this transformation. Their structures, made largely of carbon fiber composites, combined lightness with durability, reducing maintenance cycles and increasing efficiency. Cabin pressure and humidity were better regulated, improving passenger comfort while minimizing fatigue on both human and machine. These were aircraft built not only for endurance but for balance between strength and flexibility, speed and sustainability. Engines reached a new plateau of refinement. High bypass turbofans became quieter and cleaner, operating at extraordinary levels of thermal efficiency. Advanced coatings and materials allowed turbines to withstand temperatures exceeding the melting point of their components, cooled by precise internal airflow. The result was propulsion that extracted nearly all usable energy from fuel, translating chemistry into thrust with minimal waste. Every engine cycle was monitored digitally, analysed for anomalies long before they became faults. Inside the cockpit, the relationship between pilot and system evolved further. Full fly-by-wire was now universal in commercial aviation. Electronic flight bags replaced paper charts, and continuous data links provided real-time updates from meteorological satellites and ground control. The aircraft operated as a node in an interconnected web of information, aware of its own health, route, and environment. Artificial intelligence began to assist in route optimization, fuel planning, and predictive maintenance. The airplane was becoming self-aware in a limited, functional sense, capable of interpreting its own data to preserve safety and efficiency. The passenger experience also reflected the quiet precision of modern flight. Noise levels dropped, vibration decreased, and fuel efficiency allowed longer, uninterrupted routes. Non-stop flights between cities separated by entire oceans became normal. To most travellers, flight no longer felt like exploration. It was seamless transit through a managed sky. Yet beneath that smooth surface lay millions of calculations each second, adjusting control surfaces, balancing loads, and monitoring the behaviour of invisible air currents. Environmental science began to shape aviation policy with greater urgency. The industry's contribution to atmospheric carbon became a central concern, and international bodies set goals for emission reduction and alternative propulsion. Research intensified into electric and hybrid electric systems, hydrogen combustion, and sustainable aviation fuels. The physics of lift and thrust remained unchanged, but their energy sources began to diversify. The central question was shifting, from how to fly to how to keep flying responsibly. By the close of the decade, aviation had reached an equilibrium between mastery and transformation. The mechanics of flight were complete. The challenge now was ethical and environmental. Aircraft had become near-perfect expressions of applied physics, machines of precision guided by software and sustained by data. The sky itself had become mapped, managed, and understood. Yet even within that control, the essence of flight persisted, the steady balance of forces that lifts metal and humanity alike into the calm above the earth. The 2020s opened under conditions that tested the global aviation system in ways no technology could fully prevent. The COVID-19 pandemic brought air traffic to an abrupt standstill, grounding thousands of aircraft and pausing the rhythm of a world that had come to depend on uninterrupted motion. Yet even in suspension, aviation demonstrated its resilience. Aircraft carried medical supplies across continents, while engineers used the lull to re-evaluate safety, sustainability, and purpose. Flight had become so integral to modern civilization that its absence revealed how much the world relied on the quiet efficiency of the skies. When travel resumed, it did so under new priorities. Digitalization deepened further as contactless systems, biometric verification, and real-time health monitoring integrated with existing flight operations. Automation expanded to reduce physical interaction, from boarding gates to cargo management. The science of aviation now encompassed not only mechanics and aerodynamics, but also epidemiology, logistics, and behavioural modelling. The aircraft cabin became part of a broader health and data network. Meanwhile, sustainability moved from research to regulation. Governments and industry committed to net zero carbon targets by mid-century. Engineers intensified work on alternative propulsion. Electric flight, once experimental, entered early service in small regional aircraft. Hybrid systems used batteries for climb and descent, reducing emissions in the most fuel-intensive phases of flight. Hydrogen power advanced through both combustion and fuel cell designs, each addressing different scales of aviation. These technologies revive fundamental studies of thermodynamics, cryogenic storage, and energy density. The science of power itself re-examined through the lens of flight. Aircraft efficiency continued to improve through subtle aerodynamic and material innovations. Laminar flow surfaces reduced drag by maintaining smooth airflow longer across the wing. Composite manufacturing evolved with automated fibre placement, producing structures lighter and stronger than ever. Sensors embedded within airframes provided continuous health monitoring, turning maintenance from scheduled inspection into predictive intervention. Every rivet, joint and fibre became part of a self-reporting system. The use of data expanded beyond individual flights. Machine learning algorithms analyze global flight patterns, optimizing routes for fuel use and weather avoidance. Air traffic control began shifting toward digital sky management, guided by satellite constellations rather than ground-based radar. Each aircraft communicated autonomously, adjusting separation and speed to maintain flow. The invisible architecture of the air grew more intelligent and less centralized, a distributed network governed by mathematics. Public perception of aviation also evolved. Passengers sought transparency about environmental impact, driving airlines to disclose fuel efficiency and carbon offset data. The experience of flight, once a symbol of freedom, now carried awareness of its environmental cost. Yet within this awareness emerged innovation, a determination to preserve the human capacity to move through the air while respecting the planet beneath it. By the midpoint of the decade, flight had entered a phase of reflection as much as progress. The science was complete, but its application was being reshaped by global values and ecological necessity. The sky remained the same, governed by pressure, density, and lift. What changed was humanity's understanding of its place within it, not as conquerors of the air, but as stewards of its delicate balance. As the 2020s progressed, the focus of aviation shifted toward integration with emerging technologies and new operational concepts. Urban air mobility, once a theoretical pursuit, began to take tangible form. Electric vertical takeoff and landing vehicles, or eVTOLs, promised to connect cities in minutes rather than hours. Their development relied on principles familiar from traditional aerodynamics, but with new challenges in energy density, noise reduction, and autonomous control. Engineers studied lift distribution across multiple rotors, thermal management in compact propulsion systems, and the aerodynamics of low-speed hover transitioning to forward flight. These aircraft would not replace conventional airliners, but complement them, forming a layered system of air transportation from neighborhood to continent. Artificial intelligence became an essential component of operational management. Autonomous taxiing, automated route planning, and predictive maintenance relied on real-time processing of massive data sets. Aircraft learned to anticipate turbulence, adjust for weight distribution, and optimize engine performance autonomously. Safety margins could be calculated continuously, creating a dynamic environment where every flight was monitored not just by pilots, but by a collective intelligence spanning sensors, servers, and algorithms. Environmental engineering remained a central concern. Hybrid electric propulsion, hydrogen fuel, and sustainable aviation fuels became more than prototypes. They entered active service on regional routes. Aerodynamic refinements focused on drag reduction, laminar flow optimization, and variable geometry wing components. Every kilogram saved, every percentage of efficiency gained, reflected decades of cumulative understanding in fluid mechanics, thermodynamics, and structural science. The physics of lift remained constant, but the energy required to sustain it began to diversify. Air traffic management began to evolve in parallel. The implementation of satellite-based navigation and communication allowed dynamic routing, enabling aircraft to adjust trajectories in real time for efficiency, weather avoidance, and traffic density. The sky itself became a managed environment, a network of moving nodes communicating autonomously while humans supervised overall flow. The era of centralized control was giving way to distributed, adaptive management systems. Passenger experience also evolved subtly. Cabin designs emphasized comfort and energy efficiency, integrating advanced ventilation systems, adaptive lighting, and ergonomic seating. Quiet, smooth flights became the standard, reducing physical stress and cognitive load. The act of flying approached the seamless. Passengers moved through airspace supported by physics, engineering, and global infrastructure operating invisibly. By the end of this period, aviation had entered a hybrid phase between tradition and transformation. Jetliners continued to carry millions over vast distances, while new aircraft explored urban, regional, and autonomous domains. Flight remained governed by the timeless balance of forces, lift, drag, thrust, and weight, but the systems that controlled and optimized it had grown far more complex. The human role persisted in supervision and decision-making, but the machine now possessed its own capacity for observation, calculation, and adjustment. The sky had become not only a space for travel, but a managed ecosystem of physics, technology, and intelligence working in quiet coordination. Entering the late 2020s and approaching the 2030s, aviation began to embody a synthesis of all prior knowledge, combining advanced materials, autonomous systems, environmental engineering, and human-centered design. Aircraft were no longer isolated machines but nodes in a global network, operating with both predictive and adaptive intelligence. The science of flight, the study of air, lift, thrust, and drag, remained unchanged, yet its application had become increasingly nuanced and efficient. Electric and hybrid propulsion matured, extending range while reducing emissions. Turbofans evolved with higher bypass ratios and adaptive nozzle designs, allowing quieter, more fuel-efficient flight. Hydrogen combustion engines and fuel cells entered limited commercial service, introducing new challenges in cryogenic storage, thermal management, and safety systems. Engineers revisited fundamental thermodynamics to optimize these novel energy sources, while aerodynamic refinements minimized drag and improved lift-to-weight ratios. Every system operated in coordination, balancing energy, structure, and environment to sustain flight with minimal impact. Autonomy advanced alongside propulsion. Aircraft became capable of fully automated takeoff, cruise, and landing under supervision, guided by real-time sensor networks. Machine learning algorithms continuously adjusted for turbulence, load distribution, and weather changes. Air traffic management evolved into a dynamic, distributed system in which every aircraft communicated with others to maintain optimal spacing and routing. The sky itself functioned as a coordinated network, with physics, software, and human oversight intertwined seamlessly. Urban air mobility progressed from prototypes to small-scale implementation. eVTOLs and autonomous shuttles began connecting dense urban centres, reducing congestion and integrating with conventional airliners for multi-layered transportation networks. These vehicles required precise control over hover and transition aerodynamics, careful energy management, and real-time collision avoidance, blending classical principles of flight with computational intelligence. Passenger experience was refined with science and human factors in mind. Cabin environments were optimized for air quality, temperature, noise reduction, and ergonomic comfort. Automated systems monitored passenger safety and well-being, subtly adjusting lighting, pressure, and humidity. The act of flight became nearly imperceptible, with the technical complexity concealed behind the quiet stability of engineered forces. By the end of this period, aviation had achieved a form of equilibrium. Speed, efficiency, and range were optimized. Environmental impact was actively managed, and human-machine collaboration reached new levels of sophistication. Flight remained the same physical phenomenon that had fascinated humanity for centuries, yet the methods, systems, and infrastructure supporting it had become far more integrated, intelligent, and adaptive. The sky had transformed from a space of conquest into a space of stewardship, guided by knowledge, precision, and continuity. As the 2030s approach, aviation stands as a testament to centuries of observation, experimentation, and refinement. The physics of flight, the steady balance of lift, thrust, drag, and weight, remains unchanged, yet humanity's mastery over these forces has grown extraordinary. Aircraft now operate within a layered ecosystem of systems, combining advanced materials, intelligent automation, satellite navigation, and environmental management to maintain flight with unparalleled efficiency and safety. Sustainable propulsion has become central. Hybrid electric and hydrogen systems supplement traditional turbofans, while battery technology continues to improve energy density and discharge efficiency. Engineers study the behavior of materials under extreme thermal and mechanical stress, ensuring that every component, from wing spars to turbines, operates reliably under a wide range of conditions. The science of energy, once abstract, now drives the very mechanics of flight. Autonomous systems and artificial intelligence have transformed operations. Aircraft adjust continuously to environmental variables, optimizing trajectories, lift and fuel consumption in real time. Air traffic management functions as a distributed network, coordinating thousands of flights simultaneously while maintaining safe separation and efficiency. Pilots and operators supervise, interpret, and intervene when necessary, but the aircraft itself executes complex calculations with millisecond precision, responding to forces that humans can only perceive indirectly. Urban air mobility and regional autonomous transport have become integrated extensions of global aviation. Electric vertical takeoff vehicles, designed for low-altitude corridors, complement long-range jets, creating a multi-layered system that maximizes both connectivity and efficiency. Lift, drag, and thrust are managed in novel configurations, requiring careful attention to rotor aerodynamics, transition stability, and energy storage, while remaining consistent with the fundamental physics that has guided flight for centuries. Passenger experience reflects this integration. Cabins are optimized for comfort and efficiency, controlling pressure, air quality, lighting, and vibration. The act of flying feels effortless, a seamless experience underpinned by millions of calculations per second. The environment, invisible yet pervasive, ensures safety, stability, and continuity across every mile travelled. By the culmination of this history, aircraft have become more than machines. They are living systems of physics, engineering, and information. The sky itself functions as a managed, intelligent network, and flight is no longer merely a human achievement, but a coordinated balance between human intention, machine precision, and the immutable forces of nature. What began with birds and gliders, with hot air balloons and wooden wings, has evolved into an era where flight is both ordinary and extraordinary. A quiet, continuous mastery of the air that carries humanity smoothly, efficiently, and responsibly across the globe.